Good morning, everybody. Does everybody have a pair of glasses? Fancy, stylish glasses. Ooh, all right. I was trying to give you some of the history of quantum mechanics here and atomic models. We had this problem, right, where Rutherford's model wasn't, it had some features that weren't quite right, especially with those electrons that were supposed to be crashing down into the nucleus that weren't. So we're going to try and fix that problem today. And in order to understand the fix, we have to go back to Planck and his black bodies. So remember, Planck was studying those black bodies and determining the energy of the photons. And one of the things that had sort of led Planck to wanting to study these black bodies and these photons and their energies had something that was discovered in the 1860s, which was the line spectra of gases. So I brought with me here a device that will let me electrify gases. This is a thing that's got a transformer in it. It bumps it up. What does it say? Doesn't say. High voltage. I'm pretty sure it's about 5 to 10,000 volts. Just knowing what I know about gases. And I have some gases here in my little sample container. Let's see, let's do this one. So what's in this glass tube is a gas, an elemental gas from the periodic table. I've put it into the high voltage shroud here that is going to electrify. So we're going to put high voltage from one end of this tube to the other end of this tube. And we're going to see what comes out. What have I given you here? Do you remember what these were? Yeah, diffraction gratings, right? So these glasses have a rudimentary diffraction grating in them. And we're going to use that diffraction grating. Remember, diffraction gratings spread light out, okay, into its constituent parts. Would you guys mind getting up and actually closing the doors, because the bleed of light can interfere. So we'll put you in the dark, which is pretty normal, right? Always in the dark in physics. How do I not die? Where's the not die button? Somewhere right there. Okay. So take a look at the spectra through the groovy glasses. Maybe take your glasses off and look at the color all by itself. And then look through the groovy glasses and see if you can't sort of convince yourself that the color that you see without the glasses is made up of the colors that you see with the glasses. You're looking at a fingerprint, right? You're looking at what's called a line spectra. Does anybody know what this gas is? Yeah, neon, good job. Okay, so I gotta use my neon lamp here. Let's do, not that one. That was boring. That one's, oh yeah, we'll do this one. Okay, so now, I do my best to not die. Might get me out of doing my chores this afternoon, but the other negative effects. Okay, here we go. You see that one? Or are we getting any bleed from my iPad? Are you guys able to see the line spectra okay? Yeah. Okay, right? So this is mercury. Okay, mercury vapor lamps, that kind of stuff, street lamps, have this gas in it. But the pattern of lines should look very different, okay, from what we had before with the helium. Okay, come on in, don't trip. Let's see, where's the one I wanted to do? Yeah, we'll do this one. Okay. All right, here we go. Perhaps the most studied line spectra ever. Do you see 3 colors? maybe a fourth, maybe just maybe. Probably 3. The fourth would be really faint, and these glasses may not be able to resolve it. Okay? Does anybody know what this is? Most studied element in the universe? Hydrogen. Helium's 2, hydrogen is number 1. Okay? Right? But this is hydrogen gas. Okay? And this hydrogen, right, gives off that characteristic line spectra that you're seeing through the groovy glasses right there. Okay, here come the lights. I'm going to turn the lights on. Here it comes. All right. All right. So, if you would pass your glasses up, we'll collect them here. So I wanted you to see those because they're going to be really important for understanding what's going to happen next. Thank you. More glasses. These line spectra, like I said, were well known in the 1860s. And nobody could explain why these spectra existed. They were very literally fingerprints for these elements. In other words, if you mix the elements up, you would see both of the line spectra superimposed on each other, but you could definitely tell there was a relationship. There were very specific frequencies and wavelengths of light that were coming off for these things. And the question from the 1860s onwards was, where were these things coming from? Why did they exist? Why was there this characteristic spectra of lines coming off of these things? And it wasn't just emission spectra, okay? So here's hydrogen and mercury and neon. This right here is the hydrogen absorption spectrum. So you could take a sample of hydrogen gas in a tube, hold it up to like sunlight, and if you looked at it through a diffraction grating, there would be black lines, okay, where there would be emission. Exactly the same frequencies are being absorbed as were being emitted. So electrify it, and the light would come out. Hold it up to the rainbow, to white light, and those frequencies would get absorbed. Nobody could figure out why this was happening. But one thing that did happen is a mathematical description for the relationship between all of these wavelengths and frequencies. So these are the wavelengths in hydrogen, the visible ones, 410, 434, 486, and 656. At first glance, it doesn't seem like there is any kind of relationship there. They're not like doubles or halves or quarters or thirds of each other, any of that sort of stuff. But in the 1870s, a high school physics teacher, now we say high school nowadays, it was probably more like the first 2 years of college, but nonetheless, a high school physics teacher by the name of Balmer, last name Balmer, came up with the mathematical description for the relationship between all of these wavelengths. He discovered that the inverse of the wavelength was equal to a constant. We'll get to that constant here in a second, okay? And now I'm going to write this a little funny. Balmer didn't exactly write it this way, but I'm going to write this as 1 over 2 squared, which to anybody else would usually be 4, right? But we're going to write it as 1 over 2 squared for reasons that will become apparent, or you may have already guessed if you've been in chemistry, okay? Minus 1 over n squared. And this n is an integer, okay? So that when you put in n equals 1, you would get like the 610, okay? And then n equals 2, you get the next one. N equals 3, so on and so forth, okay? Going on down the line, okay? But even though Balmer had mathematically described the relationship between these emission spectra, and this is for hydrogen only. He wasn't able to explain why. So again, we had a mathematical fit, okay, but we didn't understand why the emission spectra was happening and why it worked out according to this relationship. This constant, it's called the Rydberg constant, is 1.097 times 10 to the 7 inverse meters. Okay? And this series, this mathematical series, is called the Balmer series, and it corresponds to the experimental series that you just saw through the Glooby glasses for hydrogen. So we can calculate exactly where those lines are going to occur. But again, nobody knows why. Fast forward now back, okay, to Rutherford's model, and we start having this convergence of ideas. We've got the Planck-Einstein relationship for the energy of a photon. We've got Marie Curie and her husband Pierre and Henri Becquerel playing around with radioactivity. We've got Rutherford's model of the atom, planetary model of the atom that needs some fixes. And the person that would be able to put it all together was Niels Bohr. Okay? Niels Bohr was a Danish scientist and physicist. In 1912, Bohr was he was finishing up his doctorate degree, University of Copenhagen, and he would visit Rutherford's lab in England, and would get sort of just really, really excited about the work that Rutherford was doing, and he took his energies in the scientific space and just poured them all into trying to figure out Rutherford's model of the atom, why these electrons had these special orbitals, and in 1913, okay, he came up with the Bohr model of the atom. And I could at this point say it was the first model of the atom and I could tell you all about it, but that does not speak to the incredible story that is the story of Niels Bohr, and more particularly his wife, because we are indebted to his wife for the Bohr model of the atom in a way that might come as a surprise to you. Because Niels Bohr, as smart and brilliant as he was, really couldn't write anything down to save his life. Like we suspect that he had a very severe form of dyslexia. His written communications were a dumpster fire. He got through life by dictating letters that other people would write down. That's how bad his writing was. To get through school, in high school and in college, Bohr would go to lectures, sit and memorize what he was hearing, and go home and dictate to his mother his notes that he would then study from. Like, that's how bad his disability was when it came to, like, the written language. As he started going through college, right, you can imagine that just the technical knowledge that we required, like, how do you dictate an integral or a derivative or tons of math, right? This is what Bohr had to do. He had to, like, talk the math out, and his mom would have to try to get down, right? So she would have to learn rudimentary calculus and all that kind of stuff. Well, as Bohr matured and, started dating and got onto Tinder and everything else, right? Met his future wife, his fiancée would start taking over the role where his mother had played in his earlier years. And Mrs. Bohr would come to be a pretty good mathematician in her own right. just trying to, understand the math that her husband was dictating to her, making sure that she could get it down correctly, the syntax and the method and all that kind of stuff. So Bohr's model of the atom happened like this, right? He's trying to think about Rutherford. He's finishing up his doctorate degree. They have been married now at this point, and they are about to embark on their honeymoon. So they're brand new newlyweds. They're about to embark on their honeymoon. Tickets for the train. They were going to leave for a month. They were going to leave Denmark for a month and go tour Europe. And Bohr comes home, screaming at the top of his lungs, "We have to write this down. We have to write this down. We have to write this down." And Mrs. Bohr is like, "What is going on? Are you okay?" And he's like, "I have figured it out. I know how to fix it. We have to get it written down." And so she reaches for her quill and paper and parchment and all that kind of stuff and gets ready. And he says, "Honey, it's going to take 3 days." They were supposed to leave on their honeymoon the next day. Mrs. Bohr looked at her husband and said, "Go." I want you to know they eventually made it onto their honeymoon. But they did delay, and we have Mrs. Bohr to thank for it. She recognized how important this was, right? And she got it down as he dictated it to her over the next 2.5 days. Okay? Right? So, the story of Niels Bohr is incredible on a lot of fronts. For those of us that have learning disabilities, it's a ray of sunshine. It's a story about human weakness being turned into strength as you work around the different ability you might have. Bohr would go on to become the Underground Railroad for scientists during World War II. A suspicious number of Jewish and German scientists would go visit Bohr in Denmark and then suddenly disappear, only to reappear in the United States. And Bohr was smart enough or lucky enough to always escape the Gestapo's probing spies. Stories about Bohr and his son rowing people across the North Sea to meet up with British submarines in the North Sea to smuggle scientists out. Just some incredible tales of heroism, right? In a time when the world was absolutely falling apart, and he himself would be able to escape the Nazi persecution. There's so much going on surrounding all of this. If you ever get a chance to read biographies of these scientists that worked like on the Manhattan Project, it's amazing. It really is absolutely incredible. So what was it that Bohr did, or what was it that Bohr figured out? This is a summary, okay, of what took place over 3 days. But essentially, Bohr had hit upon an idea. And this is the first quantum model of the atom, and a model that incorporated this idea, started by Einstein and Planck, that energy can only come, in discrete chunks. There's no wheelchair ramp of energy, it's stairs, right? And what does that have to do with atoms? Bohr made the conceptual leap that Rutherford's orbits, the electrons going around, had to have something special about them. And the thing that was special is that their orbital energies were quantized. In other words, there wasn't an infinite number of orbits that could exist in an atom. There were only very specific orbits that could exist. And those orbits were quantized or determined by the angular momentum of the electrons in their orbits. There was something special about the angular momentum of an electron in its orbit that made it stable. that made it so that the electron didn't decay in its orbit. And the orbits themselves were orbits where energy was not being radiated away. Now, I want to point out that Balogh himself was not able to explain why. He is theoretically predicting what these orbits need to be, but he has no mechanism, no explanation for why these orbits are special, other than, well, their angular momentum must be quantized. Moreover, transitions between these energies, these orbits, would involve a quantum jump, a transition of energy without the electron being in the intervening space. Bohr's energy levels in hydrogen, he would determine, well, Mrs. Balogh would write them down for us, okay, would follow the following pattern. The energy of the nth orbital, okay, would be equal to negative 13.6 electron volts divided by n squared. In other words, the first energy level is negative 13.6. So because negative 13.6 divided by 1 squared is negative 13.6. And then if you put in n equals 2, you would get the negative 3.4. And for the n equals 3, you get the negative 1.5, and so on and so forth, right? Balogh is able to calculate what value the energy for the orbits in hydrogen had to be in order to be these special stable orbits. And then, knowing what these special energies were, he was able to calculate how much energy an electron needs to be able to transition, say, from the first orbital energy up to the second. It's going to be the difference between these two levels. So let's transition between the second and the third. Let's just say an electron, like in my gas tube here, right? This is hydrogen. I give it some electricity, which gives enough energy for an electron to transition from the second orbit to the third orbit, right? So that's, we're going from negative 3.4 to negative 1.52. Well, negative 1.52 is bigger, right? Right? Negative 1.52 is a more positive number than negative 3.4. It's always has messed me up because 3.4 is a bigger number, right? It's negative, right? So everything's backwards. Okay? So if we take negative 1.52 minus a minus 3.4, we get the difference between those two things, which I can't do in my head. Let's see what that is. I think this is a number I'd have memorized. 1.88. Okay? So the delta energy between these two states is equal to 1.88 electron volts. That's the amount of energy an electron needs to be able to go from 2 to 3. And as far as Balogh is concerned, it's also the energy that's required for it to fall from 3 to 2, right? Either way. But any other difference in energy that does not exactly match a transition between allowed orbits simply doesn't happen. It's not allowed. They're not observed in nature, and mathematically, they're not going to happen because the angular momentum isn't the right value. So Balogh sets out to calculate all of these things, right? And comes up with that relationship that I gave you, okay? And what's more, links together this change in energy, my example 1.88 eV, and realizes that that energy has to either come from somewhere or get, like the electron has to either gain that energy to jump up, or it has to release that energy to come down. Let's talk about releasing energy. If an electron's going to go from the third to the second energy state, it's got to give up 1.88 electron volts worth of energy. Well, where's that energy going to go? Turns out 1.88 electron volts, that energy, gets turned into a photon with a very specific frequency and a very specific wavelength. It just so happens to be the 610 nanometer wavelength of the first line in the Balmer series. And then the 4 to 2 is the next one, the 5 to 2 is the next one, so on and so forth, all the way down. Bohr calculates the mathematical relationship between these energy transitions in hydrogen and comes up with the following equation, which looks an awful lot like the Balmer series, doesn't it? Bohr has finally explained why the Balmer series exists. The Balmer series, that series of colors that comes out of hydrogen and their mathematical relationship is the direct result of electrons leaving higher energy levels and falling to lower energy levels within the hydrogen atom. They emit very specific, indeed characteristically significant lines in that spectrum that exactly match Balmer's mathematical model as well as Bohr's mathematical model of the atom. The lines in the Balmer series are transitions. Bohr also discovers that the Balmer series is not the only one. Remember how I wrote the Balmer series as 1 over 2 squared minus 1 over n squared? Turns out the Balmer series exists for all transitions that end at the second energy level. For electrons that are jumping down to the first energy level, it's a different series, and the energy there is so high that those exist in the ultraviolet region of the spectrum and we can't see them with our eyes. And it wouldn't be till the 1920s and 30s that ultraviolet detectors would be good enough to be able to measure those wavelengths. But then there's other transitions from like 3 and above, so 4 to 3, 5 to 3, 6 to 3, so on and so forth, right? That would all end up in the infrared portion of the spectrum. So not only is Bohr able to explain the Balmer series, the visible series that comes out of hydrogen, but he's also able to explain the other series that would later come to be discovered as scientists were able to measure them with better and better equipment, okay? So Bohr coins some terminology here that's going to be important for us moving forward, okay? He talks about ground states and excited states. The ground state would be the lowest energy level possible in an atom. And then any electron that's not in that lowest energy level, if it's in a higher energy level, is going to be in an excited state. The transitions, right, that are taking place between these orbits are instant. The electron, this picture sort of implies, right, that the electron moves through the intervening space. That is not what happens, okay? It is in one orbit and then it is in another orbit. Instantaneously, the energy being pushed out in the form of a photon of specific frequency. And so again, in the Balmer series, right, it's these transitions. Any transition that takes us from anything above 2 down to 2, where the 3, 4, 5, and 6 are in the visible portion of the spectrum. The 7th one actually pushes a little bit into the ultraviolet portion of the spectrum. We can't see it with our eyes, okay? And then, as I said, those other series would be discovered. Bohr predicted them. And this is an exact agreement, right? This isn't just like, Bohr's 5% off or whatever. Like, he's absolutely nailing where these frequencies and wavelengths are going to show up in all of these series, which means that Bohr's model for hydrogen is really, really good. It has very strong predictive power, but there are some issues. And again, Bohr's smart. Like Rutherford, he knows that there are problems with the model, okay? Namely, there's still not a mechanism for why these electrons are orbiting but not radiating energy. Bohr knows that these orbits are special. He doesn't know why. Other than it has something to do with the angular momentum, okay? He has no mechanism in his model for how these jumps occur. Like, what's the mechanism that actually causes the electrons to move, right? And it's only good for hydrogen. Bohr's model doesn't work for anything else on the periodic table. And what else is on the periodic? Okay, so we're good, right? Like 99% of the universe is made of hydrogen, right? So we explained 99% of the universe. We're doing good, right? But hydrogen isn't that interesting. Let's talk about the things that just make you and me. Of all the elements on this table, what are the most important ones that make up you and me? Carbon, nitrogen, oxygen, one more, phosphorus. Okay? Those are the building blocks of us. Okay? It's really, really important. And then there's a little sprinkling of some other things. It turns out that things like selenium and zinc and copper and stuff like that in these micro amounts do matter for us. Okay? But let's face it, to get from hydrogen even just to carbon, that's a lot more electrons and protons and neutrons that are going on there. And Bohr's model can't do that. You can cheat a little bit, okay? Because you can do Bohr's model for helium if you singly ionize helium. What does it mean to ionize an atom? Yeah, we're losing, we're like pulling electrons out of it. So if we do helium and we have it lose an electron, well, helium only has 2 to start with, right? So we lose 1, we have 1 electron. Well, that's just like hydrogen, right? And you can kind of like, what if we doubly ionize lithium? Well, lithium has 3 electrons, right? And if we doubly ionize, it means it only has 1 electron, and it looks like hydrogen, right? See the game we're playing here, right? Okay, but getting anything above doubly ionized anything's really, anyway, it's messy, okay, right? But, and here, this is the big deal, okay? Bohr's model is the first one to incorporate this idea that you must quantize the energy. It's a quantum model, different from the classical model that Rutherford came up, because Rutherford's orbits were unlimited. You could really have electrons in any orbit. Bohr comes along and says, nope, I have good reason to believe that they're quantized. They're quantized in their angular momentum, and then when he does that, he's able to show that it lines up exactly with the Balmer series and the other series and all that kind of stuff. And then we come to Schrodinger. Yes, cat guy Schrodinger. Okay. Oh, I forgot to bring it. You know what? I'm gonna be right back. I have to show you. forgot this. Right? Everybody gets it, right? Yeah, the scary part is I understand. Right? Okay? The thing on my shirt here, okay, and I know it's hard to see from the back, right, is Schrodinger's equation for the hydrogen atom expressed in spherical coordinates. Okay? This is quantum mechanics. Okay? And the shirt reads, what part of, and then a really lots of messy math Schrodinger equation don't you understand, right? Okay? We had these made up back when I was in college, and we wore them around because we were nerds. This is the back side of the shirt. On the front side of the shirt, okay, we put Maxwell's equations in their integral forms, okay? And it says, and God said, Maxwell's equations, and there was light in Genesis. Okay, in religious university, we were having a lot of fun, right? So yeah, but like, I'm about to talk about this. You're not going to see this math, right? But we have to come to grips with what Schrodinger said about how atoms are working, and this is what this is going to do. Is we're going to fix Bohr's model. So while Bohr's model is the first quantum model, and it's got really good predictive power, and I think I've given you homework about calculating some energy transitions and stuff like that, it doesn't work for anything except hydrogen. But Schrodinger's equation does. So here's the thing. Bohr, even though he has the first quantum model, is still treating electrons like he had been trained to treat electrons. What are electrons? They're particles, right? They're little they're a piece of charge, right? And they zip around and they don't. What Schrodinger and others do, now I need to be careful here. Schrodinger was not the only person to come up with ideas like this. There were actually two other formulations of quantum mechanics that are equally valid in terms of explaining what's going on. In 1932, Bohr and Einstein and Schrodinger and Dirac and Pauli and like 30, 40 physicists, all quantum mechanics in the world, all got together. They all met in Copenhagen, and they had a conference. And at the conference, they simply decided. They just kind of said, you know what? We've got three different ways of explaining the same thing. Let's pick one. So the interpretation I'm giving you today is called the Copenhagen interpretation of quantum mechanics. It's the one that physicists have standardized on in terms of how we describe what's going on here. But just realize that we had some choices to make, and this was the best one. You'll have to trust me that it was the best one, because it's about to get weird, okay? What Schrodinger does is he says, okay, look, we know electrons aren't just particles, they're waves. So what happens if we try to take Bohr's quantized model, but put de Broglie's hypothesis of electron matter waves and squish this all together? What ended up happening is that Schrodinger discovered standing waves, electron standing waves in three-dimensional space. This diagram right here is depicting rather loosely, okay, what a standing wave in three-dimensional space of an electron might look like around the nucleus of a hydrogen atom. What did I just say? Okay, have you guys come to grips with the fact that electrons can be both waves and particles? Electrons have wavelengths and all that kind of stuff? Okay, just go with it. Okay, like those of you that are still skeptical, just assume that it is, okay? Why are these orbits in the Bohr model so special? They're the only ones that can form standing wave patterns. When we studied standing waves back in physics 2A, they could only exist on certain lengths of, say, string at certain frequencies and wavelengths. If we didn't get the right frequency and wavelength for a length of string, it just kind of all collapsed. And what Schrodinger realized is that an electron is trying to travel as a wave around one of these orbits, but if the circumference of that orbit wasn't exactly the right size, the wave couldn't form its standing wave pattern. It would just fall apart. And so Schrodinger treats electrons as waves and then sort of deals with the consequences. And one of the consequences that we're forced to think about is what does it mean for an electron to have a wavelength? What does it mean for an electron to have a wave function? Like physically, what is it? It turns out under the Copenhagen interpretation that this is a probability function for what the electron is doing. I can tell I've totally lost you because it's all straightforward, isn't it? I mean, like, duh. It's obvious. What am I trying to say? Does anybody have a quarter, a coin? Something I can flip? Oh, okay. Okay, I would like everybody to witness, right? Eliana has given me a quarter. This is a, what is this? Ellis Island. I didn't even know they made it. I thought it was all states. Okay, a 2017 Ellis Island. Is that what that is? Quarter. Okay, and this will be the quarter that she gets back. No money is going to change. Okay, right? All right. So I have here a quarter, right? Okay, and I am going to turn this quarter, okay, into a probability function. Okay, I'm going to try to express the existence of this quarter as probability, much like Schrodinger is doing to electrons in, so I'm going to turn the quarter into a quantum thing, okay? Right now it's a particle, but I'm going to make it quantum, okay? The way I'm going to do that is I'm going to flip this quarter, okay? And I'm going to hide it. Is it heads or is it tails? You were pretty sure. It's heads, okay?
Tails.
Tails?
Tails.
Tails? How sure are you?
100%.
Hundo. Okay. Right. Okay. But are you really 100% sure?
Yes.
Yeah. Okay. Just going for it. I love it. I love it. Right. Okay. Right now, this quarter can only accurately be expressed as the superposition of two probable states. Heads or tails. Okay, so a coin can be heads or it can be tails, right? Okay, and what I'm saying is, right, the probability of this coin being heads or tails has to add up to 1 or 100%. Okay? And so, in order for this to add up to 1, and knowing what we know about coin flips, what's the probability that it's heads? 50% or 0.5, right? And what's the probability that it's tails? Also 50%, right? Okay, so if I have this quarter, right, here on my arm, right, we know it exists, right? It's here. There's no doubt that it exists. But if we don't directly observe what state it's in, then we are forced to concede that it is 50% heads and 50% tails. And what kind of object, what kind of thing can only exist as a superposition of functions? What kind of thing can only be at the same place at the same time? A wave. I have turned this quarter into a wave. And I know, you're sitting there going, Sabine, that's stupid. Okay? The quarter's right there, right? We know it's heads or it's tails. You just haven't shown us, right? But what I'm trying to help your brain understand is that without directly observing the state that it's in, physics can only say that it is 50% heads and 50% tails. Notice I can't say it's 100% heads and 0% tails because I don't know that, right? I have to fall back on a probability, a statistical probability of what's going on, right? So what happens when we directly observe it? It goes from being a superposition of two things to what? One or the other, doesn't it? And what kind of things are one or the other? Particles. Are you ready? That was a stupid magic trick. I stuck it in my pocket. Okay, right? So let's do it for real, right? Okay. Because it does exist, right? Okay, but right now we can only describe it as 50% heads, 50% tails until we go in and observe it. It's heads, right? And now it's a particle. I can describe it with particle probabilities and functions and specific states, but when it is flipped and covered over and we have no precise information, then we're forced into thinking about it as a wave, not a like physical matter wave, but a wave of probabilities, probability states, right? I'd like everybody to see that I'm giving Eliana back her money and that no bribery is taken place. Okay, what is all this? Okay, when you have this interpretation of probable states and what that means, and physicists are still arguing to this day whether or not there's anything physically real about this or not, like are these probabilities like real, or is there something else going on? That's actually not as interesting as what's happening. You end up with functions that describe these probability states, and you end up with three sets of functions, of which I'm only showing you the first set, okay? These are the radial functions. There's also spherical functions and some of the others, right? But you see how they kind of numbered these? Don't worry about anything that's happening over here. See how it says radial 1, 0, and then radial 2, 1, and then radial 2, 0, and then radial 3, 2, 3, 1, 3, 0. A pattern emerges in the map, in the functions. The functions are big and nasty and do all kinds of weird stuff, but a pattern of quantum numbers, like 2 and 1 that get applied to all these different things, start falling out. And it's these patterns that give rise to the visual interpretation that you guys know as orbitals. Quantum mechanics defines a probability cloud. These radial functions that I showed you give us a probability of where an electron might be within a given region of space. That cloud, its density, the higher the density, like here towards the center, the more likely you are to find an electron in that space. And as it gets more rarefied towards the outer edge, you're less likely to find it. And so what we did in physics is we said, look, the cloud is kind of hard to visualize or even think about in those things. Why don't we just take the probabilities that represent 90% of the volume that we're likely to find the electron in, and simply call that the place where an electron might be. Niels Bohr, Schrödinger, others, they had a near infinite number of choices for the name that they could have picked for this structure, right? They could have called it a basketball. They could have called it, I don't know, a sphere. They could have called it a carrot. Anything would have been better than the term orbital. Because as soon as I say the word orbital, what picture pops into your brain? That is not what an orbital is. An orbital represents the region of space where you are likely to find the electron 90% of the time. But what about the other 10% of the time? The answer is, meh. Don't know, don't care. But 90% of the time, you're likely to find it somewhere in that region of space. They look like basketballs, don't they? I mean, why not just call them spheroids or something? Why orbital? I mean, I know why. It was Rutherford's orbits and they were carrying over the terminology. Anyway, hindsight's 20/20, right? But it turns out that those different radial functions that I showed you predict different sizes for these things. And so they needed a way to kind of start labeling what they had. They noticed that there were symmetries and repeated patterns within there, and so they started calling the ones that were spherical, they started labeling them s orbitals, okay? But if you had, like, say, an electron in its ground state at its lowest energy level, it would be a small sphere. And then, like, the next energy level, the probability functions would tell you it would be more likely to be found in a higher energy, like a further distance from the nucleus. And then they just started calculating these things out. Again, just sort of the natural consequence of applying the mathematics of waves to electrons in Bohr's model of the atom, sort of mushing all of these models together, quantum ideas, wave-particle duality, everything coming together. Who needs drugs? I mean, I know I've said that before, but I'm going to say it again. Like, who's on what? Right? To get this. I mean, okay, spheres I'm good. Bow ties, I mean, Schrödinger liked bow ties. I can kind of explain that, right? Okay? But then we start getting like four-leaf. So these are the orbital shapes that are predicted by the mathematics of quantum mechanics. Okay, jumping over all of that, okay, right? This is the, do you remember the wave function for electromagnetic waves? There was like a differential equation, sort of wave equation that gave rise to all the sine cosine functions for wiggles. This is the wave equation for quantum mechanics. Okay, it's the function that, this is the equation that generates the functions that I showed you, I didn't show you all of them, for all the electrons that exist in every atom on the periodic table. The nature of that equation is that it is a partial differential equation, and mathematically we can only solve second order differential equations. It basically means we can solve hydrogen and helium like by hand using mathematical symbology. Once you go to third order partials and above, okay, so like for example, carbon would be a sixth order differential equation. Anything above second order differential equations cannot be solved analytically by hand. They can be solved numerically in computers. You have to make approximations and sort of converge to answers. So they're solvable in the sense that computers can do it, but it's not something that like mathematically we can tie up in a nice neat little bow with an answer. But the predicted shapes of these orbitals, a clown committed some serious crimes with balloon animals, is like all I can say, right? Now, the sphere I get, do you see those yellow ones right there? Okay, this is like the second kind of orbital that popped out of the mathematic. It looks like a bow tie. The probability that the electron will be found near this, and by the way, the origin of all of these things, the place where they all come together and they show those axes, that's where the nucleus is, okay? So this describes the space around the nucleus of the atom. And whereas the s orbital up there, the top spherical one, says that the electron can be pretty, close down to the nucleus, those yellow ones called the p orbitals show that there's a 0 probability for being at the center, right? It's either going to be in one of the two lobes, okay, of that bow tie. And then these next ones, okay, the red ones are called d orbitals. So it goes s, p, d, f. And if you've taken chemistry, you're starting to recognize some of this terminology. SPD, why that? Why SPDF? Does anybody know what happens after F? G. What comes after G? H. What comes after H? After, for some reason, we went SPDF, GHIJ, right? Okay. Skipping over S and P, okay, because we already used those. SPDF are the letters of the German counting words for 1, 2, 3. 4. And then after that, we just sort of gave up. But yeah, that's why S, P, D, and F. Anyway, we can, the way that you picture, okay, these orbitals as existing is they're kind of all overlapping each other. But instead of, like in the Bohr model, having discrete, like this is the energy level for this electron and only one electron can go up and be in the next energy level, with the quantum mechanical model of the atom, we have electrons existing in all of these orbitals simultaneously. So we can have electron in the 1s, and another one in the 2s, another one in the 2p, and so on and so forth. Okay? And these functions are all overlapping each other. They don't sort of exist separate from each other, right? They all share the same origin of coordinates, which is the nucleus. And the rules, the quantum numbers, okay, that exist, there isn't just one quantum number the way that the Bohr model had. Remember, Bohr model just had the n value, right? The energy level, and that was it. Schrodinger's model of the atom has 3. And it would pick up a 4th that was unexpected, that was not predicted in the Schrodinger model of the atom, but would come later, okay? But let's try it. If your brain is has shut off already, I wouldn't blame it, number 1. Number 2, I'm going to throw you a lifeline, okay? I'm going to rescue you from the doldrums of quantum mechanics, and we're going to have a surprisingly concrete way of figuring out where electrons are in atoms, okay? We might get there by the end of today, right? So just hang on for the ride, because I've got to tell you what the rules are, and then we can start applying the rules, and you're just going to see that this actually flows, all right? So Schrodinger's model, we end up with n. We had this before, right? In the Bohr model, the atom was counting the energy. We're going to call that the principal quantum number. And then we're going to use the symbol L to talk about another quantum number called the orbital quantum number, and then n sub L is going to be our orbital magnetic quantum number. These are the names that they called it. Again, I would have picked something different. But notice the rules. So first of all, n, just like n we've always had before, 1, 2, 3, 4, whatever, right? It's an integer number, just going. the mathematics taught us and predicted that the values of L will always take on integer values starting with 0 and going up to n minus 1. So this rule was predicted by Schrodinger's equation. So what does that mean? If n equals 3, what are the possible values for L? Where does it start? 0, and then, what's the next number? 1, and then 2, and can we go to 3? No, we have to stop at whatever n minus 1 is. And since with n was 3, that means L can be 0, 1, or 2, right? That's the rule. M sub L is always negative L, including 0, up to positive L, all the integer values. So if L is equal to 2, then what are all the possible values of M sub L? Negative 2. What's the next integer? Negative 1. Don't forget 0. 1 and 2. So it turns out M sub L can do that range and takes up 5 values. Don't matter, I'm going to help you with this, don't worry. Okay? But those are the rules. There are some symbols that are used that are a little bit depreciated, but I see them crop up every once in a while. N, the principal quantum number, there is a shell symbol, KLMNOP. Don't worry about this. I bring it up simply to mention that if somebody on a video somewhere starts talking about the M shell, what they're referring to is n equals 3. Okay? More importantly, you know these are the ones that we really need to know because these are in common usage, right? If L equals 0, that means an S-type orbital. You see a quantum number L and it's 0, that's S, that's the spheres, okay? If you see L equals 1, that's a p orbital. Those are the bow ties, okay? D orbital is going to be the 4-leaf clovers and some weirdness, and then the F orbitals are just weird and all that kind of stuff. So we've got N, we've got L, we've got N sub L, and then we had a 4th quantum number that was forced upon us because of experimental data that was coming out. And it's called spin. Continuing the tradition of naming things exactly wrong. Okay? Because as if quantum mechanics wasn't hard enough, we had to, start putting ideas into people's heads. It turns out that electrons have this 4th quantum property, and it was called spin. And so if I tell you that an electron spins, what picture do you get immediately in your head? A basketball, right? Spinning around on somebody's finger or something like that, right? Okay. What's an electron? I don't want to know anymore. It's not a particle, right? It doesn't spin. It's a wave. Waves don't spin, they wiggle. What are we calling the spin? Well, it turns out that electrons have angular momentum. I'm sorry, they just do. And what kinds of things have angular momentum? Things that spin. That's Niels Bohr. That's Wolfgang Pauli. They're staring at a child's toy called a top. Right? Back in the day, before there was internet, you had to get actual physical objects out and throw them around. Okay? And one of those toys was a piece of string that you wound around a kind of cone-shaped wood object. You would throw it, and it's kind of like a yo-yo. It would sort of spin out, but it would detach at the end, and then it would sit there and spin, right? And you came up with all kinds of games where you kind of threw yours against somebody else's, gladiatorial combat and all that kind of stuff, right? But they're looking at this thing. They're looking at this top spinning. It was Wolfgang Pauli that would discover the property of spin. And it's the 4th quantum number that we have to assign to a electron's quantum state. So as it turns out, there are 4 descriptors that we need in order to accurately know where an electron's going to be 90% of the time. The analogy I like to use for this is the analogy of an address. So back in the day before the internet, you used to be able to write letters, right? And if you want to get a package or a letter to somebody, let's say you wanted to send me some hate mail, okay? And you want it to be perfectly anonymous, right? So you're gonna you're gonna sign it, you're gonna cut out all your magazine letters and paste it all together and write all that stuff, right? Okay, you're gonna mail it to me. So in order for it to make me here at work, in order for your letter to arrive, what key pieces of information do you need to put on the address label? Okay, so it needs to be addressed to somebody, right? Okay, so there'll be some sort of name, right? Mr. Balogh. Destroyer. Okay, all right, so that's who it's going to go to. And then on the next line, what do you have to put? Like a number and like a street name, right? We have streets and then there's a number assigned to the position of the building on that street. Okay, so that's going to be 1101 East University Avenue. Okay, so that's like street and the number on the street. Okay, and then on the final line, what do you need to put? Good. It's zip code that needs to be there. Everything else is actually an added extra for the humans to read. Okay? The zip code will actually determine what's going on. But you need city, state, zip code. Okay? And I guess, country, planet, arm, Milky Way, galaxy, universe. Just in case you're in parallel universes or something. Right? No. Okay, we don't need all that information, right? We really just need this stuff. So really kind of 4 pieces of information here, right? Okay. The person, because there could be more than one person at this address, right? Okay. And then we need like the number and then the specific street, because there could be other addresses that are 1101, right? Okay, but they're probably not on East University Avenue. There could be 1101 West University Avenue, right? That kind of thing, right? And then finally, really because the zip code encodes this. Have you ever been scared when you're typing in stuff to an online form that you're trying to order something and you type the zip code in and it instantly knows where you live? It's not magic, they just okay, right? So you need 4 pieces of information in order to accurately describe where this letter has to end up. These 4 things, N, L, M sub L, and M sub S, are the 4 quantum numbers that are necessary to accurately describe the address of an electron in an atom. That's what we're boiling all of quantum mechanics down to, right? This is a set of quantum address numbers that follow a very specific set of rules that I've taught you. So let's try to get through, okay? Uh-oh. It's so easy to forget some of this stuff. Okay. Here's the rule when it comes to spin. Okay. Oh, and I don't know if you noticed, how do we label spin? Well, it's MS, but like what number do we give it? It's either half or negative 1/2. We'll talk about spin later when we get to particle physics. But there are other kinds of particles that aren't just spin 1/2 particles, although electrons are spin 1/2 particles. Don't worry about why. We often just call them spin up and spin down. Positive 1/2, negative 1/2, spin up, spin down. Okay. Wolfgang Pauli taught us that, well, number one, that we needed spin. Number two, and when Wolfgang Pauli sort of proposed this idea, there was a lot of reaction along the lines of, well, who ordered that? Like it was unexpected. But again, the experimental evidence was showing that yes, N, M sub L, and NL and M sub L all existed, but within a specific orbital, there was actually room not for one electron, but two. So every one of those S, P, D, and F orbitals wasn't just one electron's probability, it was two electrons' probability. The only difference in the electrons being this spin factor. And so I present to you what I like to call the beaker of quantum mechanics. Okay? I like to think of this structure as something I'm going to fill. I'm going to pour electrons into this quantum beaker, and they are going to make up every element's electron configuration on the periodic table that I could possibly get. Each one of these lines corresponding to a very specific address within my atom, starting with the very simplest and lowest of the quantum addresses. So for the n equals 1, the very first or ground state level, okay, I have n equals 1, which means L is going to be equal to what? By the rules, what does L have to be equal to? 0, right? It's got to be 0 and then up to n minus 1. But with an n of 1, that means L can only be 0. And L equals 0 means it's an s orbital. And then therefore m sub L is from negative L to positive L going through 0. But since L is 0, m sub L is just 0. And then for every m sub L, there's spin up and spin down. So that line right there, this 1s line, 1 for the energy level, s because of the orbital type, the L equals 0, and then a line representing a place for 2 electrons to live. And that's it. That's all we can have in the first energy level according to the rules of quantum mechanics. When we get to the second energy level, our n value is 2. So what do our L values become? 0 and 1. 0 is an s orbital, 1 is a p orbital. We already know the s orbital is home to 2 electrons, so we just put 1 bar. And then when we get to the p orbital, those are 3 different m sub L's, negative 1, 0, and 1, each one having spin up and spin down, so it's home to 6 electrons. And so since every one of my lines is home for 2, I just draw 3 for the home for the 6. And so basically this cup, this beaker, okay, is the visual representation of applying the rules of quantum mechanics and the quantum numbers that come out. What I will do on Thursday is I will show you how to fill this beaker properly, being able to always predict where electrons are going to end up. And that's going to help us explain why chemists have really bad hair, which is going to explain why this periodic table looks as crazy as it does. And I will see you then.
I know, right?